25% times, or raised to the second power, since we'll have 0.25 times 0.25 times 0.75 times 0.75. So it'll really be 0.25 squared times 0.75 squared. And each of these, although they're in different orders, 0.25, 0.75, 0.25, 0.75, doesn't matter what order you multiply in. So we'll basically have 6 multiples of 0.25 squared, 0.75 squared. So that will come out to be, well, let's see, 6 times 0.25 squared plus, or sorry, times 0.75 squared, and we get a combined probability of 0.211. So we'll round it to that. Now keep in mind that this should all add up to 1 here in the end. Now we're going to look for instances where there are 3. So we can see we're kind of running down on the number of possibilities still remaining, but we've got a couple to go. So where are there 3 brokens? Well, there's one there, one situation there, another situation there, and another situation there. So these have 3 brokens. There's a 25% chance of each. So we'll have 0.25 to the third power times 0.75. Really, this will be to the first power because we only have 1 not broken. And we have 4 of those appearing. So 4 times that probability. I'll just write the whole thing out. Will give us 4 times 0.75 raised to the third power times 0.25. Oh, I'm sorry. I have those backwards. 0.25 and 0.75 should be in the other order. So 25 and 75. Okay, I hit enter and I get a combined probability of about 0.047. So 0.047. And well, there's only one situation in which you get all 4 broken, and that's the situation that you get all 4 that are broken. And that's right there. The chance that 1 is broken is 25%, times 0.25 times 0.25 times 0.25 is really just 1 multiple of 0.25 to the 4th power. And that's going to be 0.25 raised to the 4th power gives us 0.004. Well, let's see. Let's just double check, make sure we've accounted for everything, because if these don't add up to something very, very close to 1, we could be in trouble. Meaning that we've missed something. They should never add up to like 92%. That means we're probably missing something or we made a mistake somewhere. So this very tedious process plus 0.004. And we can see we get 0.998. That's 99.8%. We did a little bit of rounding, so if we had rounded further, I'm sure we would have gotten a little bit closer to 1, but that's very close, so I wouldn't say that that's due to anything we did incorrectly. It's just that we rounded. So we want to know what is the expected number of broken eggs, or boxes with broken eggs. Well, that's going to be the number times the probability plus the number of eggs times the probability plus the number of eggs times the probability. So I'm just going to do this in my calculator. I won't write it out. Plus 1 times 0.42 plus 2 times 0.211, the probability of having 2 broken boxes, plus 3 times 0.047 plus 4 times 0.004. And so we would expect, on average, to have 0.999. Well, these are broken boxes, so I'll call these 0.999 broken boxes on average per shipment, since this is just 1 shipment of 4. So if you were to ship 4 out all the time, you'd expect 1 box to be broken. Now you might say, well, do you have to go through all this work to get that? This is actually what's called a binomial experiment, something that will be addressed later on in the ebook. What you can actually do is, since there are 5 outcomes, of these 5 outcomes, the average value would be 5 times 0.25. Excuse me, I think I have this mistaken.